Hello everyone, welcome to this channel. And in this video we'll continue chapter number 12, kinetic theory of gases. Okay, so लास्ट वीडियो में हमने इस चैप्टर में बात की थी जब हम काइनेटिक इंटरप्रिटेशन ऑफ टेम्परेचर की। हमने देखा था जो टेम्परेचर है इट इज़ ड्यू टू द kinetic energy of the molecule of the gases, because the molecule of the gases, they are in motion and they have kinetic energy, so this is the reason for the contribution of temperature. इसका रिवर्स भी बोल सकते हैं कि जब टेम्परेचर जितना ज़्यादा होगा उतनी ही काइनेटिक एनर्जी भी होगी। ओके, और एब्सोल्यूट ज़ीरो की भी बात की थी, दैट इज़ द टेम्परेचर 0 केल्विन, जहाँ पर काइनेटिक एनर्जी of the molecule ceases, the velocities become 0. Okay, and so we now we'll do this topic, the law of equipartition of energy. Okay, so let's begin this from ncert. So basically I give you an idea what is the meaning of this law. So it just says that the energy of a molecule, if we are considering a molecule, then it will be distributed over its degrees of freedom. What is a degree of freedom? So basically a degree of freedom is, we can define degree of freedom in two ways. One way, okay, so if I say I'll have a particle here, a molecule here, okay, so how many coordinates are required to specify its position? So I require 3 coordinates, that is x, y and z coordinate. So 3 coordinates are required to specify its position. Similarly, if I have 2 particles, okay, then how many coordinates I'll require to specify its position? Okay, so you see here we have, they are related, they are constant. Okay, there is a relation between them. If I move this will automatically move here. Okay, so in order to define its position, I will need 3 for this coordinate, this particle, 3 coordinate for this and 3 for this, but I have to subtract 1 because in one way they are connected, there is a relation between them, they are constant. Okay, so the how many coordinates are required here? It is 6 minus 1, 5 coordinates are required. So degree of freedom for a diatomic molecule is 5. Okay, now in the other way to define this degree of freedom is, okay, so again for the first particle, the monoatomic particle, the monoatomic gas, we'll see that in how many ways this particle can execute motion. Okay, what kind of motion it can execute? So we can see clearly that this particle can move in this direction, translation motion it can execute. Okay, that is, the particle can move in either in a straight line. Okay, so in how many direction can it move in straight line? It can move in x direction, it can move in y direction, and it can move in z direction. So in 3 direction it can execute translational motion, so it will have 3 degrees of freedom. Okay, again talking about a diatomic molecule. Okay, so in how many ways, how many rotation, how many motion this diatomic molecule can execute? So we can see again, just like the monoatomic molecule, it can execute translation motion in the 3 direction, x, y and z direction. Okay, but it can also execute rotational motion in this and this direction. Suppose it is in the x-axis, okay, and it can execute rotation along like this, okay, in the y-axis, and also in the z-axis it can also rotate. It's a little difficult to make you understand this with the help of this drawing. Okay, so I'll just add a video in the description of the animation of how this monoatomic diatomic they move, they execute rotational motion. That will make your understanding clear. Okay, so but I am sure that you have got an idea so what degrees of freedom are. So basically what this, now we are ready to understand law of equipartition of energy. So it states that the energy of the system, okay, of the molecule. I'll just say that, okay, we'll see this in two ways. We'll first see by the example of a molecule and also for a mole of gas. Okay, that is, in 1 mole we have Avogadro number 6.022 into 10 to the power 23 particles. Okay, so if I take a one molecule, so I told you that for a one particle, okay, so how many degrees of freedom are there? 3 degrees of freedom. So its energy will be distributed equally in each of the degree of freedom. Okay, and how much energy will be in the each degree of freedom? It will have half kBt. This, and what is this kb? This is the uh, Boltzmann constant, and T is the temperature. So it will this much of energy, and each degree of freedom will contribute this much energy. So the degree of freedom will be at total energy for a monoatomic molecule will be half kT. Okay, so now we'll just continue from the NCERT. I give you an idea about what this law is. So let's understand this from NCERT. The kinetic energy of a single molecule is E epsilon T is equal to half mvx square plus half mvy square plus half mvz square, where vx, vy and vz is the velocity of the molecule in the three direction, x, y and z direction. Okay, so the total energy will obviously, total kinetic energy will be contribution from all the three directions. For a gas in thermal equilibrium at temperature capital T, the average value of energy denoted by the symbol is average of half mvx square plus average of half mvy square plus average of half mvz square, and this is equal to 3 by 2 kt. Okay, so we have taken the, okay, now see the velocities of the different molecule will be different. There will be not this, it not be the same for all the particles. Okay, so what we are taken the average. Okay, the average velocity, average energy, average kinetic energy in the three direction. Okay, and this, their sum will be equal to the 3 by 2 kt. This we have done in the previous paragraph. If you have not seen that paragraph, just go check it out how we come up with this derivation. Okay, 3 by 2 kt. Since there is no preferred direction, equation implies, okay, so because it will not be, it can move in any direction in the three direction. Okay, so we can clearly see that 3 by 2 kt is the total energy. Okay, so we can say that it will be distributed in the three direction. The energy, kinetic and average kinetic energy will be distributed in the three direction. So this is each, you see each direction how much energy each direction will get. This is half kBt each direction. Okay, and this is the equipartition of energy. A molecule free to move in space needs three coordinates to specify its location. If it is constrained to move in a plane, it needs two, and if constrained to move along a line, it needs just one coordinate to locate it. Okay, it's very clear. I have also already told you. Okay, if a particle is there and it is to move in a coordinate, okay, uh, okay, free to move space. For a space it need three coordinate. For a plane, in you coordinate geometry, what you do, you need only two coordinate in a plane, and if it moves in a straight line, it need only one coordinate to locate its position. This can also be expressed in another way. We say that it has 1 degree of freedom for motion in a line, 2 for motion in a plane, and 3 for motion in space. Okay, motion of a body as a whole from one point to another is called translation. This is also clear to us. A body which is moving as a whole from one point to another, that is translation motion. Okay, this is the basic definition of translation. Thus, a molecule free to move in space has 3 degrees of freedom. Okay, because we need 3 coordinates. Okay, it can move in 3 directions, so it will have 3 degrees of 3 translation degrees of freedom. Okay, each translation degree of freedom contributes a term that contains square of some variable of motion. Okay, half mv square and similar terms in vx and vy. Okay, so as I told you that each uh, each motion, each direction is contributing some energy. This is equal to half kt. Okay, and now uh, in we see that in thermal equilibrium the average of such terms is half kt. Okay, uh, both both way we can say half kt is we have come from the formula, and each from the basic formula of the kinetic energy half vmx square was there. Okay, so each term, each energy, each motion is contributing this much of energy. Okay, so this is the equipartition of energy. Molecules of a monoatomic gas like argon have only translational degrees of freedom. Okay, monoatomic have only translational motion. Okay, single atom, I told you in the beginning of the explanation. But what about a diatomic gas such as O2 or N2? A molecule of O2 has 3 translational degree of freedom. Okay, so you see again diatomic, this is also given here. Okay, in diatomic, how many motion they can do? They can do 3 translation, that is very clear in the 3 direction. But also they can, here you see it is moving along this axis, this 2 axis they can also rotate. Okay, in x, and if it is in the x axis it can rotate along to the y axis and z axis. Okay, so there are 2 contribution from the rotational side also. So total 5 motion are there, 3 translation and 2 rotational. A molecule of O2 has 3 translational degree of freedom, but in addition it can also rotate about its center of mass. Figure shows the 2 independent axes of rotation 1 and 2 normal to the axis joining the 2 oxygen atom about which the molecule can rotate. Okay, this is shown in the diagram. The molecule thus has 2 rotational degrees of freedom, each of which contribute a term to the total energy consisting of translational energy epsilon t and rotational energy epsilon r. Okay, so how much will be the total energy? This is E epsilon t plus epsilon r is equal to half m vx square plus half m vy square plus half m z vz square. And for the rotational part we see we have what is the rotational kinetic energy. This is half I1 omega 1 square plus half I2 omega 2 square. What is this I1? I1 is an inertia. Okay, moment of inertia about that axis. Okay, and this is omega 1 is the angular velocity. Okay, and again this is I2 is the angular moment of inertia on that axis, and omega 2 is the angular velocity for that axis. Okay, now yeah, you see omega 1 and omega 2 are the angular speed about axis 1 and 2. You can see the axis here 1 and 2 axis. There's the angular velocity. You know the angular direction of angular velocity is perpendicular to the plane. Okay, so this is 1 and 2, and I1 and I2 are the corresponding moment of inertia. Note that each rotational degree of freedom contributes a term to the energy that contains square of a rotational variable of motion. Okay, so rotational motion we have already, this is how the contribution of the rotational motion. Okay, now we have assumed that the O2 molecule is a rigid rotator. So now we are now talking about the about discussion was for low temperature. Okay, rigid rotator, the distance between these 2 part molecules, these 2 particles, these 2 atoms were fixed, so this is rigid. But at high temperature what will happen? It will not be fixed, it can vibrate. So vibration will also contribute to energy. Okay, that is the molecule does not vibrate, This assumption, though found to be true at moderate temperature for O2, is not always valid. Molecules like CO, even at moderate temperatures, have a mode of vibration. That is, its atoms oscillate along the interatomic axis like a one-dimensional oscillator and contribute a vibrational energy term epsilon V to the total energy. Okay, so even you see for CO, even at moderate temperature, it vibrates, it has vibrational energy. Okay, and this will also contribute to the total energy. So what we can do, we can just add up this. Okay, so total energy for this kind of, for at high temperature, and for if the molecule is executing vibrational energy, the total energy will be contributed here. So translation energy plus rotational energy plus vibrational energy. Okay, this is given by, the vibration is given by half m dy by dt whole square plus half ky square. Okay, so this is the two energies. This is the vibrational energy. Okay, and now you see, this is total mechanical energy actually. Okay, half mv square plus half kx square is, okay, potential energy plus this is kinetic energy, total mechanical energy due to vibration. Okay, now we case the force constant of the oscillator and y is the vibrational coordinate. Okay, now once again the vibration energy terms in equation 12.26 contains square terms of vibration variables of motion y and dy by dt. Again, this term has the, you see, square of this. Even in rotation omega square was there and linear v square was there. Okay, now at this point notice an important feature in equation 12.26. Where is 12.26? Yeah, this is the equation that by this, yeah, the sum of the these three. While each translational and rotational degree of freedom has contributed only one square term, one vibration mode contribute two square term, kinetic and potential energy. Clearly you can see that the vibration is contributing two square term. Okay, one is obviously kinetic, half mv square, and the other one is the potential energy. Okay, so each quadratic term occurring in the expression for energy is a mode of absorption of energy by the molecule. Okay, so the each term, it tells us about the energy, the and absorption of energy, the energy it is absorbing. We have seen in thermal equilibrium at absolute temperature capital T, for each translation motion, the average energy is half kT. Okay, so this is, we have seen in the previous paragraph, the temperature interpretation of temperature interpretation of kinetic energy. Okay, so each translation mode contribute half kBT. The most elegant principle of classical statistical mechanics state that this is so for each mode of energy. Okay, and this will be proved in higher classes due to statistical mechanics, that it is not just for the translational, it is true for all the three modes, that is translational, rotational and vibrational. They all will contribute half kT. That is, in equilibrium the total energy is equally distributed in all possible energy modes, with each mode having an average energy equal to half kT. So each mode of vibration, or whether it is vibration, whether it is rotational, whether it is translational, they all will contribute half kT. This is known as the law of equipartition of energy. Accordingly, each translational and rotational degree of freedom of a molecule contributes half kT to the energy, while each vibrational frequency contributes 2 into half kT, because we have seen vibration mode consists of kinetic and potential energy. So kinetic energy will contribute half kT and potential energy also contribute half kT to kT. The proof of the law of equipartition of energy is beyond the scope of this book. Here we shall apply the law to predict the specific law heats of gases theoretically. Later we shall also discuss briefly the application to specific heat of solid. Okay, so in the next video we'll see the specific heat capacity, and we will derive the expression for that, and also the gamma, that is the ratio of the Cp upon Cv for monoatomic, diatomic and triatomic. Okay, so let's discuss that in the next video. If you find this video helpful, please give a like, share and subscribe. Thanks for watching.